Howdy folks, welcome to lesson 2.8. We're going to talk about two variable inequalities. I just noticed how weird my eyes look in this picture. So graphing inequalities in two variables is kind of like graphing lines, which you also graphed in two variables. Remember, you did lines like y equals 3x minus 2 and you graphed them. Well, x and y are your two variables. Basically, the difference is your solution. Your solutions are all on one side of that line, and it may or may not contain that line. So the line may or may not count as solutions. If they do count as solutions, then you draw a solid line. If they don't, if the line doesn't count as solutions, then you would draw a dashed line. The line is the boundary, and then the half plane. It cuts the plane into two half planes, and then you shade in the half plane that has all your solutions in it. Pickled pig's feet. That's your secret phrase. So what's the graph of each inequality? Okay, so y is greater than 3x minus 1. So the boundary is the line y equals 3x minus 1. And since it's y greater than, that means that, so let's see, y measures up and down. This is the y-axis. Y measures up and down. So if y is greater than, that means our solutions are going to be above this line. So since it's just greater than and not greater than or equal to, we're going to make a dashed line. But first, let's figure out where this line is going to go. Y equals 3x minus 1. So my y-intercept is 0, negative 1. My slope is 3, or 3 over 1, up 3, right 1. So the point 0, negative 1 is here. And then if I'm going to count off my slope, I'm going to rise 3. 1, 2, 3. Run 1. And now I'm going to draw a line that goes through those 2 points. But since it's just greater than, that means that the boundary is not included. The boundary is when y equals 3x minus 1. But the solutions to this inequality is only when y is greater than 3x minus 1. So to show that we don't include the boundary, we draw a dashed line. And then if you're using this method of saying, well, y measures up and down, and y is supposed to be greater than 3x minus 1, so we're going to shade above this, you just think about one point on that line and then go up, and that's the side you're supposed to shade. You can also do this business of picking a point on one side of the line, like 0, 0, and plugging it into the original equation. And then if it's in the area you're going to shade, then it'll be a true statement. So for example, if I pick the point 0, 0 as my test point, then I'm going to put a 0 in for y, and a 0 in for x. And I'm going to get 0 is greater than, 3 times 0 is 0, 0 minus 1 is negative 1. 0 is greater than negative 1, so the point 0, 0 is in my solution area. So I would shade where that point is. I would shade on everything on the side of the line where that point is. So there's two methods where you can figure out what side to shade on. Picking a point and plugging it in, or looking at, if you have y by itself, greater than means shade above, and then y less than would mean shade below. What about this guy? Y is less than or equal to 3x minus 1. We got the same boundary line here. So that means we're going to have the same y-intercept, and then count off with the same slope. But now it's less than or equal to, so the boundary is included. So we're going to draw a solid line to show that the boundary is included. And then y is less than, which means that we're going to shade below the line. So pick a point, go below that point, and that's the side you're going to shade. And that's how you graph those inequalities. So problem 2. This map shows the number of tickets needed for small or large rides at the fair. You don't want to spend more than $15 on tickets. How many small or large rides can you ride? Well, if I got $15, how many tickets can I buy? They're 25 cents each. So, let's see, so that's 4 tickets for $1, right? I guess the dollar sign goes over here, doesn't it? I did grow up in America. So if you can get 4 tickets for $1 and you have $15, then you can do 15 times 4 and get 60 tickets. You can buy 60 tickets with 15 bucks. So let's try to relate to this situation. I can get at most 60 tickets. I'm going to spend 3 tickets on each small ride I go on and 5 tickets on each large ride I go on. And if I add those numbers together, that has to be less than or equal to 60. So let's define. Let's let the variable x represent the number of small rides we go on, and let y represent the number of big rides we go on. So then can we write some sort of inequality or equation that models this situation? So I'm going to spend 3 tickets times the number of small rides I go on plus 5 tickets times the number of large rides I go on, and that has to be less than my total number of tickets. So 3 tickets times the number of small rides I go on plus 5 tickets times the number of big rides I go on has to be less than or equal to my total of 60 tickets. So when you have an equation that's kind of in standard form like this, you can find the x and y intercepts pretty easily. Or you can also solve for y and get it into slope-intercept form. So maybe I'll just show you both. So the boundary for our graph is going to be 3x plus 5y equals 60. That's the line that's our boundary. So if I wanted to find the y-intercept, I'd put a 0 in for x. 3 times 0 is 0, so that would give me 5y equals 60. And then if I divide both sides by 5, I get y equals 12. So that gives me the point 0, 12. If I put a 0 in for y, then I get 3x equals 60. If I divide both sides by 3, I get x equals 20. So then I would say here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 20. And that's 20, 0. And then I could just draw a line through those 2 points. Well, say you don't love graphing in that method, but you really like the slope-intercept method. Well, all you got to do is get y by itself. So subtract 3x from both sides. You get 5y is negative 3x plus 60. Then divide both sides by 5 and you get y equals negative 3/5 x plus 60 divided by 5 is 12. So you still get your y-intercept to be 0, 12. And now you can count with your slope down 3 to the right 5. So down 3 to the right 5. Down 3 to the right 1, 2, 3, 4, 5. Down 3 to the right 1, 2, 3, 4, 5. Down 3 to the right 5, and then boom, you're right there. Okay, now look back at the inequality that we wrote. Is this going to be a solid line or a dotted line? It says less than or equal to, so we're going to include our boundary, which means that's going to be a solid line. And then let's see, let's think about something real quick. Why did we only graph this in the first quadrant? Why would we do that? Why doesn't this line go over this way and down this way? Does it stop here or does it keep going? Well, what does x represent and what does y represent? The number x is the number of small rides you can go on. Can you go on -1 rides? No, you can't. Can you go on -1 big rides, no, you can't. So both x and y have to be positive. So that's why we're only in the first quadrant. So we have less than or equal to, that tells us that we include our boundary, so it's a solid line. And then less than means we're going to shade below. Well, less than only really means you're going to shade below if you have y by itself. So we would have to kind of think about if we were solving the inequality this whole time. Do we ever divide by a negative that would switch this to greater than? No. We're subtracted 3x here. We divided by a positive 5 here. So this inequality would be y less than or equal to negative 3/5 x plus 12, so we would shade below. Another way to find out would be you could plug in a point. You could plug in a point either under the line or above the line. If we pick like 1, 1 or 0, 0, if you put in 0, 0, you're going to get 0 is less than or equal to 60, which is true, which means you would shade below. If you put in 1, 1, you would get 3 plus 5 is 8 is less than or equal to 60, which is true. So any point you pick under this line is going to be true. That's why we shade under it. But check yourself, because when we shade under the line, we're saying that every single point under this line is a solution. So question, is this point a solution? Is the point 1, 1/2 a solution? Can we go on one small ride and 1/2 of a large ride? No. So since we're counting actual things here, we can only count whole numbers. So instead of shading the entire region down here, we just have to consider all the points x, y, where x and y are both integers. So 0, 0 counts. I could go on 0 small rides and 0 large rides, and I would not spend more than 60 tickets to do that. I could go on, wow, look at all those options. And all these options, each one of these points represents an x and a y value that tells you how many small rides and big rides I could possibly go on without going over 60 tickets. So this is technically the actual graph of the solution to our inequality. So any one of these points gives you a combination of small rides and large rides that we could go on without going over 60 tickets. Alright, why don't you pause and see if you got it. Okay, so we have the same sort of situation except we only have 30 bucks. So $3 times the number of small rides, or 3 tickets I mean, times the number of small rides, plus 5 tickets times the number of large rides, has to be less than or equal to, let's see, we got twice as much money, so that means twice as many tickets. 120 tickets. So now if I get the y by itself, subtract 3x, 5y is less than or equal to negative 3x plus 120. Divide both sides by 5, and you get y is less than or equal to negative 3/5 x plus 24. And if we go the intercepts way, the x-intercept means you put a 0 in for y. So we get 3x equals 120. Divide both sides by 3, and x equals 40. So there's 20 squares here, so if we count each square as being 2, then this would be 40, comma 0. And then our y-intercept would be 24. So if we count each of these as 2 also, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And that is 24, 0. And then we draw our line. And then we think, all right, we're shading underneath, but it's not everything. It's only the integer values. So, but now there's integer values in between here too. 1, 2, 3, 4. So we're just going to have a bunch, a bazillion, million, bajillion bazillion, bajillion, bajillion, bazillion little dots representing each x and y value of small rides and big rides. So there you go. Alright, let's talk about graphing an absolute value inequality. We've talked about graphing in absolute values. How about an absolute value inequality? Well, we're used to seeing y by itself, so let's get y by itself. If I subtract 1 from both sides of the inequality sign, then I get negative y is less than the absolute value of x plus 2 minus 1. And then if I divide both sides by negative 1, whenever I divide by negative, it switches my inequality sign. And then I'll have negative absolute value of x plus 2 plus 1. So that tells you that that it's an absolute value that's been translated 2 units to the left, 1 unit up, and then flipped across the x-axis. So let's take a look. Our vertex is going to be negative 2, 1. And then we would normally go up and down like this, but since we have a negative in front, we're going to go down like that. Since it's only greater than and not greater than or equal to, we don't include the boundary. So that's why our boundary lines are dashed. And then greater than means we're going to shade above. Bada bing, bada boom. So what inequality does this graph represent? Well, the vertex is 1, 2, 3, negative 2. And it goes up like normal, and it's up 1 over 1, so the slope is 1, so that means that our a value is going to be 1. It's basically just a transformation of y equals absolute value of x. The vertex is translated to 3, negative 2. So 3 to the right is x minus 3. Down 2 is minus 2 on the end. And our slope is normal. It's just 1. So 1 in front gives you this. It's greater than. It's not greater than or equal to, because our lines are dashed here. So it's just greater than, and we're shaded above. So y is greater than absolute value of x minus 3 minus 2. So see if you can figure out what inequality is represented by this graph right here. Okay, so one thing I realize is, so let's look at the boundary line. The vertex is negative, well, let's see, each line is 2 here, right? So this is actually negative 4, and then 2, 3. So the vertex is at negative 4, 3, and it's going down. We go down 1 over 1, right? So from, let's see, do we have a good point? So we go down 1 over 1, down 1.5, over 1.5, or actually it would be down 3 over 3. So we just have a negative 1 slope. So we're going to have the equation for the boundary line is y equals negative absolute value of x plus 4, and then plus 3 to get up. And now we're shaded above, so our actual inequality is y greater than negative absolute value of x plus 4 plus 3. This takes you, the plus 4 takes you 4 units left. This plus 3 takes you 3 units up. And the negative flips you upside down. The greater than says shade above, but leave the lines dashed. Go ahead and get cracking on practice 2.8, and I'll see y'all on the flip side. Bye.